Whenever we start the construction process of a building, the first step we need to do is the excavation of the foundation. And to start the excavation process, we need to know the size of the footing, which cannot be determined without knowing the load carried by the column above the footing. Since we design all the elements before starting the construction process, but in case we need to know the approximate size of the footing, then we must calculate the loads on the columns, and with the help of which it's easy to know the size of the footing. Let's consider a two-story building with 12 columns numbered from C1 to C12 and 19 beams from B1 to B19, out of which B13 and B15 are secondary beams. Let's calculate the approximate axial load on column 6, which is connected by the beams B5, B9, B12 and B8. We have the given data. Number of stories is equal to 2, floor height is 3 meter, size of primary beam is 230 into 300 mm and the size of secondary beam is 230 into 230 mm. It should be noted that primary beams are connected by columns at both the ends and secondary beams are those beams which are connected by walls or primary beams at least at one end. As you can visualize from this picture, only beam 13 and beam 15 are secondary beams, rest are primary beams. Size of column is given as 230 into 300 mm. Both external and internal walls have thickness 230 mm. Soil bearing capacity is given as 150 kN per meter square. Height of neck column is 1 meter. Height of plinth beam above ground level is 600 mm. And the thickness of both roof slab and floor slab is assumed to be 125 mm. Since we need to calculate the axial load on column 6, the total load on this column would be equal to the load transferred from the highlighted area ABCD surrounding this particular column plus the self weight of the column. In other words, we can say that the total load on column 6 would be equal to the load transferred from its connected elements, including beams, walls and slabs, plus the self weight of the column. The dimensions of area ABCD would cover half the length of its connected beams B8, B9, B5 and B12. Width of this area would be equal to half the length of B8 plus half of B9 and the total will be 4 meter. Length of this area would be equal to half the length of B5 plus half of B12 and the total will be 5 meter. Hence the area of ABCD would be equal to 20 meter square. Now let's assume some data as per the code. Live load on roof slab is assumed to be 1.5 kN per meter square. Live load on floor slab 3 kN per meter square. Floor finishing 1 kN per meter square and waterproofing load is assumed to be 0.8 kN per meter square. To calculate the total load on roof slab, we need to know its self weight, which is given by the formula thickness of slab into density of RCC. Thickness of slab is assumed as 125 mm and density of RCC is 25 kN per meter cube. On substituting these values, the self weight of roof slab will be equal to 3.125 kN per meter square. Total load on roof slab will be equal to self weight plus live load plus floor finishing load plus waterproofing load. Live load is already assumed as 1.5 kN per meter square, floor finishing 1 kN per meter square and waterproofing 0.8 kN per meter square. On substituting these values, total load on roof will be equal to 6.425 kN per meter square. Total factored load on roof will be equal to 1.5 times total load on roof, where 1.5 is the factor of safety and the total will be 9.64 kN per meter square. The self weight of floor slab will be equal to thickness of slab into density of RCC. Thickness of slab is 125 mm and density of RCC is 25 kN per meter cube. On substituting these values, the self weight of floor slab will be equal to 3.125 kN per meter square. Live load on floor slab is 3 kN per meter square. Floor finishing is 1 kN per meter square and total load on floor will be equal to self weight of floor plus live load plus floor finishing and the total will be 7.125 kN per meter square. Total factored load on floor will be equal to 1.5 times total load on floor, which will be equal to 10.69 kN per meter square. Self weight of primary beam will be equal to area of cross section into density of RCC. Area of cross section of primary beams is 230 mm into 300 mm. On substituting these values, self-weight of primary beams will be equal to 1.725 kN per meter. The factored self-weight of primary beam will be equal to 1.5 times self-weight of primary beam, which will be equal to 2.58 kN per meter. The self-weight of secondary beam will be equal to 0.23 meter into 0.23 meter into density of RCC, that is 25 kN per meter cube, and the total will be 1.322 kN per meter. Factored self-weight of secondary beam will be equal to 1.5 into self-weight of secondary beam, which will be equal to 1.98 kN per meter. To calculate the wall loads, we need to know the height of the wall. Height of wall will be equal to floor height minus depth of beam. Floor height is given as 3 meter and depth of beam is 300 mm. The total will be 2.7 meter. The self-weight of external wall will be equal to thickness of wall into height of wall into density of brick masonry. Thickness of wall is 230 mm, height of wall is 2.7 meter, and density of brick masonry is 20 kN per meter cube. On substituting these values, self-weight of external wall will be equal to 12.42 kN per meter. Factored self-weight will be equal to 1.5 into 12.42, which will be equal to 18.63 kN per meter. Since both the external and the internal walls have same dimensions, therefore the self-weight and the factored self-weight of internal walls would be same as that of external walls. Hence, self-weight of internal wall will be equal to 12.42 kN per meter and factored self-weight will be equal to 18.63 kN per meter. Now, we need to calculate the load transferred to column 6 from each floor separately. Area of slabs surrounding the column 6 would be equal to 20 meters square. Total length of primary beams surrounding column 6 would be equal to 1 by 2 times length of B8 plus length of B9 plus length of B5 plus length of B12, and the total will be 9 meter. Total length of secondary beams surrounding column 6 would be equal to 1 by 2 times length of B13, which will be equal to 3 meter. Wall length under primary beams would be equal to length of primary beams, which is already calculated as 9 meter. Since we are not providing any wall under secondary beams, therefore wall length under secondary beams would be 0. Now let's calculate the load transferred from roof to first floor. The roof load will be equal to total factored load on roof into area of roof surrounding column 6. Total factored load on roof is already calculated as 9.64 and area of roof surrounding column 6 is 20 meters square. On substituting these values, roof load will be equal to 192.8 kN. The load due to primary beams will be equal to factored self-weight of primary beams into total length of primary beams surrounding column 6. Factored self-weight of primary beams is already calculated as 2.587 kN per meter and length of primary beams is 9 meter. On substituting these values, the load due to primary beams will be equal to 23.28 kN. The load due to secondary beams will be equal to factored self-weight of secondary beams into length of secondary beams into 1 by 2. Factored self-weight of secondary beams is already calculated as 1.983. Length of secondary beams is 3 meter. On substituting these values, the load due to secondary beams will be equal to 2.98 kN. It should be noted that only half the load of secondary beam will be transferred to column 6. The load due to walls under primary beams will be equal to factored self-weight of primary walls into length of primary walls. Factored self-weight of primary walls is already calculated as 18.63 and length of primary walls is 9 meter. On substituting these values, the load due to primary walls will be equal to 167.7 kN. And since we are not providing any wall under secondary beams, therefore the load due to secondary walls will be 0. Total load from roof to first floor will be equal to roof load plus load due to primary beams plus load due to secondary beams plus wall load, and the total will be 387 kN. The load transferred from first floor to the plinth level will include floor load, load due to primary beams and secondary beams, and the wall load. Floor load will be equal to total factored load on floor into area of floor surrounding column 6. Total factored load on floor is already calculated as 10.69 and area of floor is 20 meters square. On substituting these values, floor load will be equal to 213.8 kN. The load due to primary beams is equal to factored self-weight of primary beams into length of primary beams. Factored self-weight is 2.587 kN per meter and length of primary beams is 9 meter. On substituting these values, the load due to primary beams will be equal to 23.28 kN. The load due to secondary beams will be equal to factored self-weight of secondary beams into length of secondary beams into 1 by 2. Factored self-weight is already calculated as 1.983. Length of secondary beams is 3 meter. On substituting these values, the load due to secondary beams will be equal to 2.98 kN. The load due to primary walls will be equal to factored self-weight of primary walls into length of primary walls. Factored self-weight of primary walls is 18.63. Length of primary walls is 9 meter. On substituting these values, the load due to primary walls will be equal to 167.7 kN. Finally, total load from first floor to the plinth level will be equal to load due to primary beams plus load due to secondary beams plus wall load, and the total will be 408 kN. The load transferred between plinth beam and footing will only include the load due to primary beams, which will be equal to factored self-weight of primary beams into length of primary beams. Factored self-weight of primary beams is already calculated as 2.587 and length of primary beams is 9 meter. On substituting these values, the total load will be 23.28 kN. The total self-weight of column will be equal to column cross-sectional area into height of column into density of RCC. Column cross-section is given as 230 into 300 mm. Height of column is equal to twice floor height plus depth of plinth beam plus depth of neck column. Floor height is given as 3 meter, depth of plinth beam is 0.6 meter and depth of neck column is 1 meter. On substituting these values, height of column will be equal to 7.6 meter. Again, total self-weight of column will be equal to area of cross-section of column, that is 0.23 into 0.3 meter, into height of column, that is 7.6 meter, into density of RCC, which is 25 kN per meter cube. On simplifying further, total self-weight of column will be equal to 13.11 kN. Finally, total load on column 6 will be equal to load transferred from roof to first floor plus load transferred from first floor to plinth plus load transferred between plinth beam and footing plus total self-weight of column. On substituting these values, total load on column 6 will be equal to 832 kN. Since this calculation gives an approximate value, that's why we should take an incremented value as allowance for bending due to the effect of fixity. For interior columns, we should consider an increment of 0 to 10%, for side columns 11 to 15%, and for corner columns 16 to 33%. After adding 10% of extra load to column 6, total actual load on column 6 will be equal to 832 into 1.1, which will be equal to 915 kN. So this was all about this lecture. If you want the PDF and Excel sheet of this calculation, you can check out my website. The link will be provided in the description box of this video.